Hey, welcome back. This is part 2 of our 2 lectures this week from my elementary statistics course. In this video, we're going to be going through the rest of section 3.3, which is measures of relative standing and box plots. So before watching this video, make sure you've already watched part 1. Okay. So in part 1, towards the end of the video, we went ahead and we converted a data value to a percentile. Okay, so in part 1, we started with the data value and we found the percentile of that. Okay, so we also talked about z-scores, but we aren't going to be covering any more z-scores in this video. So in part 1, we went from a data value to a percentile. In this video, we're actually going to be going in the other direction. Okay? So now that we're in part 2 of this video, we're going to learn how to do this process in reverse. So we're going to learn how to convert a percentile to a data value. Okay. Now, this is a little bit more challenging, going from a percentile to a data value. What you have to do, or at least what most people do, is they calculate what is called the locator. Okay? And then after you calculate the locator, you're going to use a flow chart from the book based on the value of the locator. Okay? That being said, once you get used to all the terminology, it's not too bad. It's just it's a bit more challenging than what we did in part 1. Okay? So let's go ahead and move ahead in these slides to where we left off last time. Okay, so last time we did z-scores, and we talked about finding the percentile of a data value. In other words, they gave us a data value, and we converted it to a percentile using this formula here. So the percentile of a data value x equals the number of values less than x divided by the total number of values times 100. Well, if we're going in the reverse direction, which is what we're going to learn today, we have to use a different formula. And unfortunately, it's a bit more complicated. So if you're converting a percentile to a data value, this is the flow chart that we're going to be looking at. Let me zoom in a little bit. Okay, so just like in the previous video, we want to sort the data if it's not already sorted. And that needs to be in order of lowest to highest. Okay? And then the next thing we're going to do after that is we have to calculate L, which is known as the locator. Okay, so the locator equals K over 100 times N. So we're going to use this formula to determine the locator. And roughly speaking, the locator is supposed to tell you where the data value is, or the two data values are, that you use to answer their question. So to go from a percentile to a data value. Okay? And then, like I said, it's a bit more complicated. So after we calculate the locator, we're going to go further down in this flow chart. And then based on the locator L, we split it into two different cases. So if L is a whole number, in other words, it's not a decimal, and it's not a fraction. If it's a whole number, then the value of the percentile is midway between the elf value and the next value. Okay, so basically you just take the average or the mean of the elf value and the elf plus 1th value, and that will give you your percentile as a data value. Okay, and then if L, the locator, is not a whole number, then we need to round it up, and then our percentile is actually just going to be whatever that number is. So the whole number above our decimal. Okay? And this is one of these instances when you're dealing with a locator and you get a decimal, you always round up. Okay? I'm not saying you always round up everything in statistics. I'm just saying with the locator, if it's not a whole number, you always round it up. And then your percentile is going to be the elf value. Okay, but an actual example might be more helpful than all of this whole flow chart. We're going to come back to the flow chart so we can actually use it. Okay, so let me switch back to this view. All right, so let's talk about this notation that we're learning here for the locator. So we said that the formula for the locator was L. Okay, so L is a locator that gives the position of a value. So for example, the 12th value in the sorted list, L would be equal to 12. And that's why it's very important that your data values are arranged in increasing order, otherwise the locator formula won't work. Okay, other notation here, N is the total number of values in the data set. Okay. K is the percentile being used. Okay, so an example would be for the 25th percentile, K would equal 25. So whatever percentile they're asking us to find a data value for, that's going to be K. Okay, N will be the total number of values. L is the locator, which helps us find the data value or the two data values, and then we average those two if there's two of them. Okay, and then P sub K is going to be the kth percentile. So we talked about this last time, this notation, but for example, P sub 25 would be the 25th percentile. Okay. So we can return to this page, but hopefully that helps a little bit with this locator formula. So the formula is L equals K over 100 times N. All right, so let's jump into an example. And down here, I'm going to go ahead and write the locator formula. So the locator that we just saw, the formula in that the flow chart is going to be L equals K over 100 times N. It's right here on the flow chart if you lose track of it in your notes. Okay, so K over 100 times N. Keep in mind that this is just going to give us the rough location of the data value or data values for the 25th percentile. Okay, so in this example, returning to the Space Mountain wait times, our favorite example in the book, if we want to find the value of the 25th percentile, P25, then remember that K is the same as this subscript. So here K is going to equal 25. Okay, so I think I'll just write that over here. K is the same as our percentile, so here K is going to be 25. Sorry, I didn't write far enough to the right, so let me write a little bit over here. So K equals 25, and then N is going to be the same as the total number of data values. So here they tell us that there are 50 sorted wait times. So that means N equals 50. Or if you're doing your homework or your quiz or your exam and they don't tell you how many data values you have, it will be a table like this, so you can actually just count. Like here we have 10 rows, 10 columns times 5 rows, and 10 times 5 is 50. So that's how you get 50 wait times. Okay, and then plugging in here to find the locator, we know that K is 25 and N is 50. So this formula is going to become 25 over 100. Okay, because K is 25 and then N is 50. So times 50. And this particular locator, you may be able to do in your head. It's not too difficult. But if the numbers get any messier, it's recommended that you calculate the locator using a calculator. So I'm going to go ahead and grab my calculator. Okay, and with the calculator, you can do it either in 2 steps or 1 step. So if you want to do it in 2 steps, you go ahead and do the division first. So I'm going to do 25 divided by 100, which is 0.25. And then I multiply that times 50, which should give you 12.5 if you've entered it into your calculator correctly. Okay, so here we have a locator, L, equals 12.5. Now the only thing to be kind of aware of here is we've just found the locator. We haven't actually found the percentile, the data value for that percentile. So now what we have to do is, unless we have the whole process memorized, we should go back to the flowchart. So with the flowchart, take a look at it again. We got our locator L is 12.5. So if I zoom in on this thing, with the flowchart, we have to decide whether L, the locator, is a whole number. So obviously, 12.5 is a decimal, and recall that a decimal is not a whole number. A whole number means a counting number, like 0, 1, 2, 3, 4, etc., but it can't have any fractions or decimals. So because we have a decimal here, L is not a whole number, which means we go down here to where it says no. So then what do? We change L by rounding it up to the next larger whole number. So if you're in the case where you have a decimal, you always round it up when you're determining, when you're using the locator. Okay, so anyway, 12.5 should round up to 13. When they say round to the next larger whole number, they mean the next larger counting number. So we're looking at the ones digit and then the next digit we don't really care about, so we always round up. So this is always going to go up. So this is going to round up to 13. Okay? All right, and then following the flowchart, the value of the kth percentile, or here the 25th percentile, is just going to be the Lth value. Okay, which here, because we got 13, that's going to be the 13th value. So L equals 13th value. Okay. So if you ever have a decimal, always round it up, and then the locator is just going to be that number. So now you just look at your data values. Sorry, I got to zoom out again. Now we go ahead and look at our data values, and because they're already sorted in increasing order here, we just have to count to 13. Well, there are 50 data values here, and then there are a total of 5 rows, so that means there are 10 data values in each row. So this is 10 data values. And then here we have 11, 12, 13. So our locator says that the data value that we're looking for is the 13th value, which is 25. It's just kind of a coincidence that the 25th percentile here is 25. That's not usually going to be the case, so don't assume that you could just use the number k that you had for your percentile to get the actual data value. Okay, but what this tells us is 25 is going to be the 25th percentile for this particular data set. Okay, so in other words, we got P25 happens to equal 25 here. Okay, so that's converting a percentile to a data value. And then if we look at the slides, we're going to see that the book got the same thing as we just did. Okay, so they calculated the locator the same way we did. They got 12.5, and then following the flow chart, since 12.5 was not a whole number, we rounded up, and that gave us 13 for the locator. And then because the data was already sorted in increasing order, we look for the 13th value, which is this one right here. So there are 10 here, 11, 12, 13. Okay, so that's the 13th value. Okay, so the locator and the flowchart can seem a little intimidating at first, but once you get used to them, you're going to find that they're not as bad as they might seem. Okay. All right, so that's an example of calculating a percentile, calculating a data value from a percentile. So going from a percentile to a data value. Okay, so before we go on to quartiles, I just wanted to do a quick additional example that's not on the slides using this same data set. So in particular, let's say instead of finding the 25th percentile, instead, let's say we were asked to find a percentile that's more challenging, like say the 56th percentile. Okay, so how would we find the 56th percentile? Let's just do a quick example of that. Okay, so example, find P56. Well, it's going to be the same process. The first thing we do is we calculate the locator. So L equals K over 100 times N. That's going to be our locator. Here, K is going to be the same as the subscript of P. So K is going to be 56. So here we would have 56 over 100 times N. And then recall in this problem, N was 50. Okay, the only reason I'm doing this example is just because it's a little bit more challenging topic than the problems we did last time, so I wanted to give you two examples of finding a data value from a percentile. So using our calculator here, 56 divided by 100 is 0.56 times 50 should give us 28. Okay, so here we get a locator, L, of 28. So L equals 28. So the thing is, 28 is not a decimal. So 28 is actually a whole number. So let's see how we would go ahead and find the data value corresponding to the 56th percentile. So once again, we're going to return to the flowchart. Okay, so returning to this flowchart and zooming in. Now L equals 28, and because 28 is a whole number, that means the answer here is yes. Is L a whole number? Yes. So now we're looking at this green portion to the right, this box over here. So if L, your locator, is a whole number, the value of the kth percentile is midway between the nth value and the next value. So the way you find P sub k is you take the average of 28 and 29. The nth value and the next value, you add them up and you divide by 2. Okay, so that's a little bit more complicated, which is why I wanted to do this example. So because our locator is a whole number, that means this is a whole number. That means we're on the right side of the flowchart in the green box. And following those instructions, P sub k, which is going to be P sub 56, is going to be really the 28th value plus the next one, which is the 29th data value, divided by 2. Okay, because that's what the flowchart told us. So when L is a whole number, the way you calculate the data value corresponding to the 56th percentile is you add the 28th plus the 29th. So that's 28, and then 28 plus 1 is 29, and then you divide them by 2. So all we have to do now is figure out what the 28th and the 29th data values are by looking at the table. Okay, so let me zoom out here and then return to the table. So looking at this table, the first row has 10, the next row goes to 20. So then the third row is what we're looking at. So this is 21, 22, 23, 24, 25, 26, 27, 28. So 28 is 35. And then we also want the 29th value, so that happens to also be 35. So we have 35 plus 35 all over 2. Okay, so the 28th plus the 29th is going to be 35 plus 35 all over 2. Now in this particular case, we happen to have the same number for the 28th and the 29th data value. But the whole reason we're using this formula is these won't always be the same number, okay? They just happen to be both be 35 here, but they could be different numbers. So the way you do this on your calculator is you add up the numerator first. So we do 35 plus 35, which is 70 divided by 2, okay? But the thing is, if you add up 2 of the same number and then you divide by 2, that's the same as doing 35 times 2 divided by 2, so the 2's cancel. 70 divided by 2 is going to give us 35. Okay, so here we've calculated P56 is actually going to equal 70 divided by 2, which is 35. So hopefully this makes a bit of sense. Hopefully it's helpful. Okay, so P56 is 35. And by the way, here P56 happened to be a whole number, but sometimes when you're using the locator, you can get a decimal for your percentile, and assuming that you followed the correct steps with the flow chart and plugged it into your calculator correctly, it's still valid if you have a decimal. We didn't see that in these examples, but I'm just mentioning it because you will see it in your homework. Okay, cool. So let's return to the slides while I erase all this. So the next thing we need to talk about is quartiles. So quartiles are actually should be very easy for most people to understand, since we've already learned what percentiles are in great detail. So quartiles are measures of location, and there are only 3 of them. So if you look at the word quartile, it sounds a lot like the word quarter, and everybody knows there are 4 quarters in a dollar. So you might be wondering, well, how come there's only 3 quartiles? Do they work differently? And, really, the answer is just, even though there are only 3 of them, they still divide the set of data into 4 groups. So they still are a lot like quarters in that 4 quarters gives us $1. It's just there are only 3 of them, and we'll see why in just a second. But anyway, even though there are only 3 of them, they still divide the data set into 4 groups, where, quartile, like quarters, there are 4 quarters, they divide the data set into 4 groups, with about 25% of the values in each group. So the nice thing about quartiles is these are all just a specific percentile. So if you think about it, if there are 99 or 100 percentiles, then you can almost just go back to the quarter example. If there are 4 quarters in a dollar, what do you think the first quarter is going to be for your percentile? Well, 1 quarter is 25 cents. So it should make sense that Q1 is actually equal to P25. And then 2 quarters would be 50 cents. Q2 is P50. 3 quarters would be 75 cents. So Q3 is going to be P75. So actually the analogy of quarters holds up pretty well in a lot of ways. So first quartile is the same as P25. Easy to remember because 1 quarter is 25 cents. It separates the bottom 25% of the sorted values from the top 75%. And when they say the bottom 25% and the top 75%, they mean roughly. It won't always be exactly 25% and 75%, but it's P25, so it's the closest number we can find to separate the bottom 25% from the top 75%. Same as P25. Okay, second quartile, Q2. 2 quarters is 50 cents, so it makes sense that the second quartile is P50. Okay, so the 50th percentile. One cool thing about Q2 is that it's actually the same as the median. So we learned about the median in section 3.1. We learned a lot of other things in section 3.1. We learned the mean, the median, the mode, the mid-range, and then the weighted mean. Those were all in section 3.1. P50 is the same as the median. Okay, so Q2 is the same as P50, which is the same as the median, and it separates roughly the bottom 50% of the sorted values from the top 50%. And the reason I keep saying roughly 50% or roughly 25% is if you think about it, if you have an even number of data values versus an odd number of data values, you might not be separating exactly 50% on the left and then 50% on the right. It might not be those exact percentages, but it's the closest we can get. Okay. Continuing with the analogy of quarters, 3/4 is 75 cents. So Q3, the third quartile, is going to be the same as P75. It separates the bottom 75% of the sorted values from the top 25%. Roughly speaking. It's not going to be exact. In the book, they give us this note of caution. Just as there is not universal agreement on a procedure for finding percentiles, there is not universal agreement on a single procedure for calculating quartiles. And different technologies or formulas may sometimes yield different results. Okay. That being said, for our class, you can just always do it the way we do on the slides and in my videos, and you'll be good for your homework, your quiz, and your exam. But it is important to note that some of these rules are arbitrary, like the whole locator thing. So there are sometimes different ways, different scientists, maybe in different countries or even different mathematicians might calculate them slightly differently. So that's all that they're warning us about here. But for us, we're going to be using the locator, which is one of the most commonly and widely accepted ways of calculating quartiles or percentiles. Okay, so before we jump into an example of quartiles, let's talk a little bit more. I wanted to talk about the 5-number summary. So the 5-number summary, once you understand quartiles, is actually very easy to calculate. So the 5-number summary is what we're going to be using to construct a box plot, which is a special type of graph that we're going to learn about today. Okay, so for a set of data, the 5-number summary consists of these 5 values. The first one is the minimum, or the smallest data value when they're sorted in increasing order. The second number is the first quartile. The third number is the second quartile, which is the same as the median. The fourth number is the third quartile. And then the last number is the maximum. Remember that the minimum is when the data values are written in increasing order, the minimum is just going to be the first data value. And then the maximum is going to be your largest data value. So when they're increasing order, it's going to be the very last data value. So it should be very easy once your values are sorted to find the minimum and the maximum. And then I will talk about the most straightforward way of finding these quartiles. So you don't actually have to use the locator when you're doing the quartiles, but you're welcome to. Just remember that Q1 is P25, Q2 is P50, and Q3 is P75. So if you want to use the locator, it should work just great as long as you follow the flow chart. But I will show you an even easier way of calculating the quartiles, which is essentially, first you calculate the second quartile, Q2, by finding the median of the entire data set. And then the first quartile is just going to be the median of the first half of the data values. And the third quartile is going to be the median of the second half of the data values. Okay. So even though it's not written in our book, I did want to write this down. So Q1, the first quartile, Q1, oops, that's a little hard to read. Q1 is going to be the same as the median of the first half of the data values when they're sorted. So median of first half of data values. And then Q3, the third quartile, is actually going to be the median of the second half of data values. Okay, so let me write that down here so I have some room. So Q3 is the median. Oops. Oh, I really should look at the screen when I'm writing. So Q3 is the median of the second half of the data values. Or if you prefer, you can just use the locator and do P25 and P75. That works just fine as well. Just takes a little bit longer. Okay. All right, so Q3 is the median of the second half of the data values. So let's go ahead and find this 5-number summary, returning to the same data set that we've been using, using the Space Mountain wait times from the book. Okay, so when you want to find the 5-number summary, just refer to this slide here. And I will show you the way I usually teach to determine these. So what I usually do is I start by determining, once they're sorted, I determine the minimum and the maximum. Okay. And then I do the second quartile, the first quartile, and the third quartile. That's the order I usually teach them in. So 10 is the very first data value, and these data values are already sorted in increasing order. So 10 is going to be the same as the minimum. Okay. By the way, my first cat that I ever owned was named Minnie. I don't know if I've mentioned this before, but I'm saying it now. My first cat was named Minnie. And then, can you guess what my second cat was named, or is named, because I still have him? Max. Yep. I'm really that much of a dork. So we've got the maximum is the very last data value when the data values are sorted in order. So here, max, the maximum is 110. All right, so minimum is the first number, which is 10. Maximum is the last number, which is 110. Those are always the easiest to calculate. So that's why I do them first. And then what we're going to do next is the next easiest number to calculate would be Q2. So recall that Q2 is the same as the median. And when they say the median here, they mean of all the data values. Okay? So if we return to this table, if we want to find Q2, remember that there are a total of 50 data values. So Q2 is the same as the median of all the data values. And the median is either going to be, if there are an odd number of data values, it will be the very middle data value. Or if there are an even number of data values, as in this case, then it's going to be the average of the two middle data values. And I'm not supposed to call it average. It's actually the mean of the two middle data values. So here we have 50 data values. 50 data values. Okay. 50 is an even number, which means that when we're finding the median, or Q2, it's going to be the average of the two middle data values. So how do we find the two middle data values when there's so many data values? Well, because 50 is an even number, you can easily just divide it by 2 to get the first middle data value. Okay, so the process is, let me, not really sure where to write here, but if you have 50 data values, they're an even number of data values. So that means we have 50 over 2 equals 25. So if we go to data value number 25, well, 10, 20, 21, 22, 23, 24, 25. This is the first middle data value, is 35. And then because they're an even number of data values, we're looking at the 25th data value and the 26th, which is the next one. And if you want to just use the locator, that works here too. You could just find P50. But I wanted to show you this way because even though it takes a while to explain, a lot of people like finding the median and they find it easier than doing the locator and the whole flow chart. Okay, so anyway, Q2 is the median, which is going to be, because there are two middle values, we add them up and we divide by 2 to get Q2. Okay, so what we're doing right here is we're trying to find Q2, which is the median, and that's going to be 35 plus 35 all over 2. So Q2 equals 35 plus 35 all over 2. Okay, and then we do know how to use a calculator by now, hopefully. So adding up in the numerator, we get 35 plus 35 is 70, and then 70 divided by 2 is going to give us 35. So that means Q2, or the median of the whole data set, Q2 is going to equal 35. All right? So we know our minimum, we know our maximum, and now we just calculated Q2. Okay. So those are the three easiest numbers to calculate. So the minimum, the maximum, and then Q2, which is the median. Okay. Now, for Q1 and Q3, like I said, you can use percentiles. So Q1 is the same as P25 and Q3 is the same as P75. But most people find it easier to use this information. So Q1 is the median of the first half of the data values. So let's go ahead and calculate Q1 now. So if there are a total of 50 data values, we already said 50 divided by 2 is 25. So that means there are 25 data values in the first half. So if there are 25 data values in the first half, if we want to find Q1, we just find the median of the first 25 data values. That's all we have to do here. So median of first 25 data values. Again, how did I get 25? Well, we knew that there were 50 total in this particular example. So that means there have to be 25 data values in the first half. Alrighty. So 25 is an odd number. And if we do 25 divided by 2, that will give us 12.5. Okay. Remember, just like when we were using the locator, if you get a decimal like 12.5, you want to round up. So that's going to round up to 13. So technically, we've already calculated Q1 today when we did P25, the 25th percentile. So we should get the same exact value. But anyway, the median of the first 25 data values, it can be kind of tedious, but if you wanted to start from the ends, you could count inward, but it might get a little bit confusing. So using the locator or just doing 25 divided by 2 is 12.5, and then you round up to 13. The median of the first 25 data values is going to be the same as the 13th data value. Okay, so 25 over 2, 25 over 2 equals 13. 25 over 2 equals 12.5, and then as we saw earlier, we round that up, so 12.5 rounds up to 13. So Q1 is going to be the 13th data value. Okay. And then here, the 13th data value, as we already calculated earlier, well, here are 10 data values, 11, 12, 13. So this 13th data value is going to give us Q1, which is the same as P25. So here that happens to be 25. Okay, so Q1 equals 25. That took a while to explain and to write on the board. But even though that took a while, hopefully now that you understand how to calculate it, it shouldn't be too bad. And then we can do the same process for finding Q3. So if you want to use the locator in the flowchart, just find P75. Otherwise, find the median of the second half of the data values. So remember, in this particular data set, we had 50 data values, which means when we're finding Q3, we need to find the median of the last 25 data values. Okay, so find the median of the last 25 data values. Okay, so once again, 25 divided by 2 is 12.5, and when you get a decimal, you always round up. So when we're looking at the last 25 data values, remember the first 25 is going to end right here. This is data value number 25. This one is data value number 26. So for the second half of data values, we just want to find the median of the last 25. So that's going to be at position 13. So we can just count. This is number 26. Including this one, we need to count to 13, and that will give us the median of the last 25 data values. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so 50 is going to be the median of the last 25 data values, which is really hopefully not too bad once you get used to it. And if you don't find it helpful to be finding the median of the first half and the second half, like I said, just do P25 and P75 with the locator, and then you should be okay. Okay, but here Q3 is going to be this number, which is 50. Alrighty. So hopefully that makes a lot of sense. So now we have the 5-number summary. So the 5-number summary in order is going to be the minimum, followed by Q1, followed by Q2, followed by Q3, followed by the maximum. Okay? But while I erase all this, let me go ahead and return to the slides, PowerPoint slides, if this thing will work. Okay, so in the book, they're saying all the same stuff that we just did. Okay, so they're just using the locator. So that's all the steps for finding the locator are on these slides. But just like us, they started by finding the minimum and the maximum, because those are usually the first two numbers that people calculate because they're very easy to calculate. It's just the first number and the last number. All right, and then the way the book found the first quartile Q1 was they used the locator. Okay, so they used the locator to find P25, which was Q1, and that gave us 25 minutes. And then they used the locator to find Q2, which is the same as P50, and that was 35 minutes. And then Q3, they got 50, just like we did, and they used that by using the same procedure to find P75. So K would be 75, and they used the locator and the flowchart. All right, so they got the same 5-number summary as we did, and just keep in mind that the 5-number summary does have to be in increasing order. So the first number is 10, which is the minimum. The next number is 25, which is Q1. The third number was 35, which is Q2. The fourth number is Q3, which is 50. And the last number is the maximum, which is 110. Okay, so let's talk about how we can use this 5-number summary to actually construct a pretty cool graph. So the graph that we can use once we have a 5-number summary is a new graph called a boxplot, or box and whisker diagram. A boxplot or box and whisker diagram is a graph of a data set that consists of a line extending from the minimum value to the maximum value, and a box with lines drawn at the first quartile Q1, the median, which is Q2, and the third quartile Q3. Okay, and a picture is worth 1,000 words. So let's actually take a look at a box plot. This is a box plot. Now, to actually construct one from scratch, the first thing you would do is you would calculate the 5-number summary like we did. And then you would go ahead and look for, the first thing you would want to do is you would want to start at the minimum and you want to end at the maximum. And then you want to construct your x-axis. Well, there's only one axis here, but people like to think of the horizontal axis as the x-axis. As long as you start at the minimum and end at the maximum, and then you just count in an even amount here. So you count. Then after you've made this horizontal axis, here they counted in 20s because it was convenient. Here they plotted 10, which was the minimum. They plotted 110, which was the maximum. And then once you have this horizontal scale, then you're able to just easily plot Q1, which is the left side of this box, Q2, which goes in the middle of the box, and then Q3, which is the right side of the box. So why is it called a box and whisker diagram by some people? Well, you know, just how a cat has whiskers. This box has a whisker on the left and a whisker on the right. That requires a lot of imagination, though. So that's why most people just call it a box plot. It's called a box plot because it has a box in the middle. Why is it useful? Well, obviously it's useful to have another way of graphing data and of graphing a data set. And a box plot is helpful because all that we're using to graph it is the 5-number summary, and it can show us whether the data is skewed to the right or skewed to the left, or if it's normal or if it's uniform. So if you look at this one, at this particular box plot, you'll notice that here is the median, Q2. Well, the tail on the right is much larger than the tail on the left. So because the tail on the right is much larger than the tail on the left, we would say that this particular box plot is skewed. And because the tail on the right is larger than the tail on the left, we would say that it is skewed right. Skewed right. Okay. So again, the tail on the right is the same as the distance from the middle, or the median, to the right side, which here is the maximum. The tail on the left is the same as the distance from the median to the left side. Well, because this distance to the right is larger than this distance to the left, the tail on the right is larger than the tail on the left, so we say it's skewed right. All right, and obviously, if we flip this entire picture around as a mirror image, then we would say it would be skewed left. So if the tail on the left is longer than the tail on the right, then we would say it's skewed left. But that's a topic that we've already talked about before, skewness. We're just returning to it now because we are seeing a new type of graph. Okay, so you can construct a box plot by hand, or you can use a computer program such as Microsoft Excel to construct a box plot. But the procedure is find the 5-number summary, construct a line segment extending from the minimum to the maximum, and then construct a box extending from Q1 to Q3 and draw a line in the box, vertical line in the box at the value of Q2, which is the median. Okay? So that's how you construct a box plot, but the good news is even though we have to construct box plots, all of the problems on your homework, quiz, and exam will be multiple choice. So you'll have 4 different graphs, 4 different box plots, and you will have to choose the correct one. So they will generally either give you the 5-number summary, or you'll have to calculate the 5-number summary, and then you have to choose the correct box plot, which is not too bad. You don't actually have to draw one by hand. Okay, so you just look at the graphs and try to eliminate graphs, and then the one that's left is the correct graph. All right, so we just talked about this a little bit, but I wanted to show you, remember earlier in the course we talked about histograms in chapter 2, and we talked about the distribution or the shape of each histogram. And this is kind of a nice illustration from the book. On the top here we have histograms, and then on the bottom we have the corresponding box plot. So a box plot can often be used to identify skewness, as we were mentioning, skewed right or skewed left. A distribution of data is skewed if it is not symmetric and extends more to one side than the other. So this first histogram, just looking at the histogram, we can see that the center of the graph is roughly here at the maximum. And we can see that the tail on the right is much larger than the tail on the left. So we call this a skewed distribution. And here we see the corresponding box plot. Here the middle is the median, or Q2, and the tail on the right is longer than the tail on the left. So this skewed distribution is once again an example of skewed right. If you want to see skewed left, we've talked about it before. It's going to be this same exact box plot or histogram, but it's going to be a mirror image, so flipped horizontally. So what does a normal distribution look like? Well, a normal distribution needs to be roughly a bell-shaped curve. So from the histogram, that's fairly straightforward to see that it's roughly a bell-shaped curve, and it needs to be roughly symmetric. Okay. So even though I'm not good at drawing, we can see that this histogram is roughly symmetric, and it's roughly a bell-shaped curve. Now with box plots, it's a little bit harder to tell the shape of the curve or the distribution, but you'll notice that with a normal distribution, this is the corresponding box plot. The median, or Q2, is almost in the middle of the graph. So it's right in the middle there. So the difference between skewed and normal is that the median is roughly in the middle for a normal distribution. And also to be symmetric, you'll notice that Q1 and Q3 are roughly the same distance from the median in the middle. Now it's not perfect, but in order to have a normal distribution, it has to be roughly bell-shaped and roughly symmetric. Obviously, with a skewed distribution, it's not symmetric. Even if it does have somewhat of a bell shape, it's pulled off to one side or pulled off to the other side. And then the last distribution I wanted to take a quick look at was the uniform distribution. So for a uniform distribution, remember that your histogram needs to have bars that are roughly the same height. With this one, there's a bit more variation than most uniform distributions, but roughly the same height for your bars is going to give you a uniform distribution. And you'll notice that if you look at the box plot, it's kind of similar to a normal distribution. It's just you'll notice that here's the median, which is roughly in the middle, and probably the only thing to note is that there seems to be more distance between the median Q2 to Q1 and then also to Q3. So these distances are a little bit larger. In other words, the box is a little bit wider, more than a little bit, quite a bit wider than the normal distribution. And that just has to do with a bell curve, a bell-shaped graph, versus a graph that's supposed to be roughly a rectangle. It's a little bit harder to see with the box plots though, but I'm glad we talked about it. So hopefully that's helpful for your homework, quizzes, and exams. So that is the end of this section. So thank you for watching all the way to the end, and good luck with your homework and your quizzes, and I'll see you in our next video.